Studying for a while now the work of Professor Norman Wildberger, who has been putting out YouTube videos for like 15 years, almost since back to the beginning of YouTube. And I've been taking his algebraic calculus course, which is available on openlearning.com, which is an approach to calculus that doesn't involve limits or infinitesimals or any kind of invocation of infinite processes. So it's very unusual, very powerful in a lot of ways, and I prepared this little presentation. I thought it would be fun to compare the algebraic calculus approach to this classical problem of finding tangent lines to a circle to how you would do it in this standard treatment of calculus. So you can see I have a picture here of a circle with a tangent, and it was known in the ancient world that the tangent line is perpendicular to the radius at that point on the circle. And Euclid showed how to construct this with the compass and straight edge. And that's how the ancients would have thought about this problem. But in a modern sense, when we are dealing with the Cartesian coordinate system and we have equations for a circle and equations for lines, then we're more interested in how can we find those equations for those lines which are tangent to the circle. So there's a couple ingredients that we're going to need. The first is the parameterization of the unit circle. I should have written the rational parameterization. So if you've never seen this equation before, this is the rational parameterization of the unit circle. Okay, and I would recommend to you to take this first term, plug it in here for x, take this second term here, plug it in for y, and with a little bit of high school algebra you should be able to confirm that it satisfies this equation. So it is indeed a parameterization of the unit circle. It gives you an exact point, which is unique compared to other parameterizations. We'll talk about that later. It can describe every point on the circle except for -1, 0. So -1, 0, which is right here, kind of serves as like a null point, okay? And we connect that point, we draw a line connecting that point through this point wherever the parameter t is on the y-axis, okay? And then where that point intersects the circle turns out to be given by that parameterization, which I showed you earlier. You can see it here in GeoGebra, the same expression. Okay. Let me just turn that line off. We're not going to be needing that anymore. So this is actually a very old expression with just a little bit of algebra manipulation. You can get to here from here. This is how the ancients would have viewed it. They would have seen n and m here as two natural numbers, two whole numbers, whereas for us t is a rational number representing the proportion between these two numbers. And this was a formula that was used to produce Pythagorean triples. So they were looking for right triangles which have the proportion of the sides can be represented by whole numbers. Okay, and you can find that using this formula. And I recommend you to give this a try. pick two whole numbers, m and n, and plug it in, and you can produce all of these Pythagorean triples. This is actually goes back before Pythagoras and was known to the ancient Babylonians. There is a clay tablet known as Plimpton 322, and it basically just contains tables of, or it is a table of like dozens and dozens of these kind of Pythagorean triples. Okay, so later on, we use something very similar in trigonometry, which were these tables containing angles and their sine and cosine and perhaps some other metrics. So this is an alternative to that, where you're just encoding proportions of sides of right triangles, and you're not really thinking about it in terms of angles. So that's one ingredient. The next thing we need is projective homogeneous coordinates. All right. So I'm just going to kind of skip through this, but this is a very deep and powerful kind of technology. Basically, we have a proportion of three numbers that is our coordinates both for a line and a point. Okay, so you might have been used to encoding a point with two numbers, right, and a line with a slope and a y-intercept. Okay, but in this case we're actually using three numbers, and they're a proportion, which means we can scale them however we want. And one of the things that allows us to is we can eliminate fractions, okay, which is nice. It shows this symmetry between points and lines in a plane, which is a huge part of projective geometry, which is where this comes from. It also includes limit points and limit lines. I won't really go over that, but if you're familiar with projective geometry, it's an advantage of this. So here's how it works. In round brackets, this is the equation for a line, okay? And we have a proportion of three numbers, and that represents the line given by this Cartesian equation here, okay? Now for points, we're going to use square brackets, and that third coordinate represents a common denominator. Like I was saying, we can use this to eliminate fractions, and you could convert it into a point in the usual sense just by dividing both the first two terms by the third term. And there's some other stuff about limit lines. The important thing for us, though, is that only the coordinates 0, 0, 0 are undefined for us, for both lines and for points. Any other proportion, any two of the terms can be 0 for us. But this, all three of them being zeros, has no meaning for us geometrically. Okay. So lastly, we have the J function. Using projective homogeneous coordinates, we can find the join between 2 points, so the line that connects 2 points, or the meet of two lines, the point where they intersect. Okay, and it's the same algorithm for both of these problems. This is one of the really powerful things about projective homogeneous coordinates. We're using, you'll see it involves a kind of a determinant from taking two pairs at a time, and it's strongly related to some ideas in linear algebra, but I won't really go into that here. So this is what it looks like. In red, you can see we have the first term, and it's produced by taking this second term of one times the third term of the other and subtracting the third term of the first one times the second term of the other. All right, so they're all this kind of determinantal kind of expression, and you can see there's this kind of threefold symmetry. I've kind of encoded it in color if you want to study that in a little more detail. But I encourage you, if you've never seen this before, again, make some points, convert them to projective geometry, make some lines, convert them to projective coordinates, and check that this works. So now we're ready to find some tangent lines. So what do? We start with two generalized points on the circle. Okay, so you can see I've converted that parameterization of the circle to a projective coordinates where this third term is in the the denominator has become the third term. Okay, and we're going to take the join function, the j function of two generalized points given by the parameters t and u. All right, this is what it looks like. There's a little bit of simplification that takes place. Again, please try to check this all yourself. I just want to try to keep this relatively brief. Okay, and so here we have an equation for a line. So let's take a look at this in GeoGebra. So here I have my other point, okay, given by the parameter u, and then this point A given by the parameter t, and here is our equation for the line between them. Okay, so you might think, well, let's just bring the points together and then perhaps we'll get a tangent line. You can see as they get closer and closer together, we're approaching what we would think of as a tangent line. Okay, but what happens when they come together? The line disappears. Why is that? Well, it's because we're getting 0, 0, 0 when t equals u. And remember, this is undefined for us. However, if we again go back to our high school algebra and think about this critically, this means each of these terms is a polynomial in two variables, t and u. Okay, so for any one of them, when we make t equals u, that polynomial becomes 0. That means t minus u is a root of that polynomial, so we can actually factor this a little bit further. All right, and this is what we get. All right, let's take a look at this in GeoGebra real quick. So here's now our new line, and you can see same idea. However, when we make u equal to t, voila, now we have a tangent line. All right, so all that's left for us to do is set t equal to u, and we get this sort of finished version of our equation. You can see it's almost exactly identical to the equation for a point. So we can see there's this symmetry between the points on a circle and the tangent lines to that point. The only difference is that our third term here is negative in the equation for the line. And so this translates to this equation for a line. Let's take a look at it real quick. I'm going to turn this one off, and now we have here. I'll turn off my other point too. We don't need that anymore. Now you can see, oh, where did you come from? Go away. So you can see where, as I change my parameter t, we have all of these parameters for a line. And there's in that symmetry between the equation for the point and the equation for the line, remember that the parameterization comes from a method for deriving Pythagorean triples. Okay, so what this means is, let's take the simplest Pythagorean triple, 3, 4, 5. You've probably seen this before if you know a little bit about the Pythagorean theorem. Okay, that means that in projective coordinates, the point 3 to 4, to 4 to 5 is a point on the unit circle, and the line 3 to 4 to -5 is the tangent line to that point. All right. Now we would normally think of this, of course, as the point 3/5, 4/5, and the line 3x plus 4y equals 5. So the equation that we've come up with for the tangent lines to the circle reveals this beautiful connection to ancient geometry and ancient number theory. And I find that very satisfying. So let's move on real quick. I'm not going to take as much time because you are probably already familiar with some of this stuff. If you're not, that's okay. So if we want to do this with conventional calculus, our problem, one of our problems at least, is that we need to write this as a function. Okay, so we need to move the x squared to the other side, take a square root, and we get this ugly looking thing. sorry I'm a little bit biased here, but and not only that, but we have to divide it in half. So now instead of this equation for a circle, we have a top half and a bottom half. Okay, but let's move on and see what happens. So to get the tangent line, first we need the slope, and we get that by taking the derivative. So we apply the power rule and the chain rule, and then we're not done. Then we have to plug that back into the equation of the line and solve for the constant term. And I've written that all out here, and you end up with these two equations. Okay, so I've put that here in GeoGebra under the parameter R now. That's not the one I want. Let's see, where is it? Okay, so as I vary R, get these tangent lines. You notice R has to be between -1 and 1. This is undefined outside of that range. Okay, because you end up taking a square root of negative. Okay, even at -1, because of our slope-intercept form, this becomes an infinite slope, or a divide by zero kind of situation, and the computer can't recognize it. So then we also have this one on the bottom, which is kind of the mirror image. So needless to say, I think there's a lot of disadvantages to that. I think it's more clunky, it's more difficult, and less beautiful. But there's another way that we could do this. We could use angle instead of writing a function in terms of x. So we have another way to parameterize this circle using sine and cosine. We can take derivatives of these, do a little differential calculus, and we get that our slope is negative cotangent of theta. Again, we have to plug it into an equation for a line and solve for a constant term, and we get this equation at the bottom. Okay, let's take a look at that in GeoGebra. This one is here, and you can see as I vary theta, the line goes around and around and around and around and around. Okay, so to sum up, let's compare these. So I think there's an advantage of the algebraic approach in the sense that it gives 1 point and 1 tangent line exactly for every rational number t. Whereas if we're using the square root or trig functions, we are necessarily dealing with approximations, because those functions end up being a kind of an infinite algorithm that you have to stop at what point, and that's what your computer is doing. Otherwise it would just crash every time you try to take a square root or a sine or a cosine of something. And then in the case of the square root, you have this limited domain between -1 and 1. And in the trig function, you sort of go around the circle over and over and over again every 2 pi. And I just think that there's a certain elegance and a beauty and an efficiency and an accuracy to the algebraic approach. You can see that we've come up with a way to get these tangent lines that does not rely on limits. So usually in a first year calculus course, students spend a long time learning about limits, and most students find it confusing and boring. And once you dig a little deeper, you find that the theory of limits is not really as solid as you might think. And you might argue that or not, but needless to say, a limit is not actually necessary to do calculus. I know that might sound like a bold statement, but I hope I've maybe whet your appetite and showed you that there are sort of other ways to solve these problems. Kind of building on that same point, this method is 100% algebraic. You can see what I'm doing every step, and it really just comes down to factoring polynomials. So I just wanted to mention this about when you're dealing with square roots and trig functions. I've already kind of touched on this, but there's an enormous complexity to how the computer is solving these problems. Okay, and there's also an infinite nature in the theoretical sense, right? In a practical sense, the computer is not running the infinite sum for sine and cosine, and they're not running an infinite algorithm for square roots. They're going up to a certain degree of accuracy and stopping. And so a lot of this is kind of obscured when you think you can just pick up your calculator and solve for these things. But the way I'm doing it here, this could be done 100% on pencil and paper. And even if you're using computers, you're using a tiny fraction of the computing power. And so I think that efficiency has a lot of value. And lastly, I would say there's a certain satisfaction or elegance for me personally that we're actually drawing on a lot of these ancient ideas, and we're using these modern technologies like linear algebra and projective geometry to compute things in a more sophisticated way. But there's a connection going back to the last 4 or 5,000 years of mathematics. And lastly, this same approach can be used to solve other problems besides finding tangent lines, like finding an evolute curve, which is something I ought to do a video on. But really, the way that we found a tangent line, that can be done for any curve that is parameterizable in some kind of algebraic notation, where you find the line of two generic points, you factor out where those two parameters are the same, and voila, like magic, you have a tangent line with no limits, with no nod to infinite processes, no kind of speculation or hand waving or anything like that. So in conclusion, I think that it's fair to say that this approach at least deserves a seat at the table. Okay, maybe you're not convinced that it's superior or that we should throw away all of calculus, which is not what I'm saying, but I think that students of mathematics ought to be exposed to this kind of approach to what is a very simple problem. And you see that the conventional calculus doesn't really have a clean or efficient way to find this tangent line to a circle, which is really, perhaps ought to be one of the easiest problems in calculus as it goes. This construction was known to the ancient world. So thanks for listening. I hope to be putting out more, going in some other tangents. that sort of build off these ideas. So please let me know what you think.